I can do about it. Since we are here, you guys all go through the trouble to come here, so let me do the lecture anyway. All right, so I was just talking about this Homer Keynes problem number one. I just put it in the code, and I was talking about these two different blocks and B with some weights given and a smooth surface is for the whole, so no friction, okay? And then the other thing they gave you, like a block travels along a circular path with a radius of 1.5 meter. The radius of this block B is given. Determine the speed of the block, this B, the speed of this block B. Okay, so obviously that's what they're asking. All right, what is given? Let's try to understand that. Okay, obviously here you have this 15 kg weight acting downward, right? And then this B at point B, you have another weight, right? Which is 2 kg, which is gonna be 2 multiplied 9.81 Newton. Now, this 15 kg weight that ultimately get transferred to this tension T on the rope. If you understand that, that's kind of tricky to understand. Um, they don't have pen or paper. Oh, yeah, I found it. Okay, so see, the block is hanging, right? So the block is hanging here, and it's attached by a rope, and that rope kind of goes through a hole. Obviously, the dining table is here, like the hole is here. So if you're gonna do the tension curve, so this block here, 15 kg, right? And then mg, in this case, say like m1, this is m1, and you see this tension T should be equal to this M1G. You understand that, right? So that basically the same tension that you're seeing it here is coming back to on the top. So basically, if you're gonna do it this way, so you have this tension, you have this tension along the pulley or the hole, whatever way you wanna say, you have this tension. So all of them are same T, right? It's just one T we're talking. Got it? Everybody? All right, so come back here. So this T that we are seeing it here, right? And this T that we are seeing, and this T is in which direction? We have these two different components, normal and tangential. Obviously, this could be a normal component, right? Remember that? So now that you have this normal component force, obviously, and you can also find the acceleration of the normal component by using this velocity equation and the rho. Now obviously this normal component, once you have found it from the force distribution equation, you can plug it here and ultimately find the velocity. Okay, so that's another way of dealing with this. You understand that, right? Okay, and then you have these forces here where you have this this normal force and this weight of this block, right? And if there is no friction, there's this tension here. So all this force, you have to take it account for what? Remember, we did the summation of forces in n and t direction. Everybody remember that? So that's all we're gonna do. So you're gonna come from that, means those two equations, the force balance equations, come from that to what? The an. Make sense? Once you have the an, then you have the velocity equation to deal with this, right? And that is the clue. That's how you should be thinking. This is a homework. Hopefully you should be able to solve it. And if you're not, then just refer to the problems that we did. Like we had like every time this summation of forces, right, in non-tangential direction. We did it, right, several times. That could be helpful. And in the book has so many examples problem. And still, if you're struggling, let me know, okay, end of this week. So we can take care of that. And the second problem, as I was saying, like I did it in class. Okay, so you do have the solutions. So not that much you got to do about it. And kind of all the problems goes similar way. Like number three. One thing here for number three, the radius, the previous problem, the radius was given, remember? So the rope is kind of moving from the center, and the center to rope and distance was problem number one. That distance was 1.5 meter, right? Here, so that this problem is a little tricky. So here, you see, it doesn't it doesn't follow through a circular path. It kind of follows through a arc, or a fraction of a curve. May put it this way. And you remember, like from last chapter, to find. You remember the rho? Is this the density of radius of curvature? They call it radius of curvature. Okay, that's the radius for part of the curve. Understand? Okay, so say like if you're following through a curved line, like it's not a circular path. So at any point, if you'd like to find the radius at any point on the card, that's what I'm referring. Okay, you'd like to use this equation. Now, this dy dx and you know what those are. Y and x is x and y is direction displacement. And if you are given with the equation for y and x relationship, then you should be easily find the value of dy over dx and finally find the rho over radius. Okay. Okay, so that's what I'd like to highlight. I don't know if I should be reading this problem. I mean, it's basically the same concept. Every time you start with this problem, this is the two equations that you should be starting with. Okay, summation of forces in Tn and direction. Okay, for this kind of problem. And if the rho is not given, you gotta go in the difficult way. This is the difficult route. Okay, you gotta find the rho this way. And you if you are given with like this equation, then finding the rho is like piece of cake, right? I mean, as long as you have a good knowledge on derivatives. How many of you have good graphs on derivatives? Pretty much everyone. Okay. If you struggle at any point, just tutoring center, they actually sent me an email the other day. They have some open house. Please check with them. Okay. Anytime you are struggling, I'm not sure because this is not part of this class. If you are struggling with derivatives, just go over there and try to do the derivative. Does anyone need help of this derivative? Or you guys are good? It was good? Feeling confident? Okay. Again, if just one or two students, you can either come talk with me. I will help you in person, or you can go to reading center. They're going to help you for sure. Okay. All right. So that's this. Then and kind of same pattern. You see here, same thing. Now these are the things you may want to take a picture of this because nowadays, I mean, today is unfortunately I don't have the recording. I can do one thing though. The recording started. I was talking with this, right? So I can actually keep this thing open, and that way you have it in record. So homework 6 hints. The same thing is kind of showed here. Okay, so let me talk about this. I mean, I anything that you're seeing here, I mean, now it's in record, so you don't have to take picture or anything. Anything that you're seeing here, everything will be on video lecture. Now, sometime past, I probably spent like 5-10 minutes already, but you just have to reel the video to this point to see this. Okay, anyway, so the first problem I was talking about it, as you can see it here clearly. Okay, you have these forces 15 kg and 2 kg. I got to explain a little bit what I'm writing here just for accessibility purpose. Anyway, and then you have the velocity v, rho, density. So rho is the radius of curvature. In this case, is 1.5 meter. Okay, and this an is the acceleration in normal direction, v is the velocity, and rho is the radius of curvature, which is 1.5 in this case. And this t is the tension, and then w is the weight, and is the normal force, t is the tangential direction, and is the normal direction. Okay, I think I kind of explained everything whatever I had written it. Number 2 is same as what we have done in class problem, a little bit probably data difference. Number 3, I was talking about it as well. So you have this rho equal 1 plus second derivative of y with respect to x. Second derivative y with respect to x modulus is in the denominator. In numerator, 1 plus dy dx square whole thing to the power 3 over 2. And then you have this y equation given, which is 1 over 8 x square, and then you can do the derivative. One time you're going to come up with the value of x by 4, and this an you already know, v square over rho, and you ultimately have to use these two equations you're seeing here, fn and ft, which is the normal force direction summation of force and tangential force direction summation of forces. And then here, obviously, on the figure sketch, you're seeing the normal force and the friction force here, the first time you're seeing, because the mu k value is given. Okay, that's why this problem could be a little challenging. Okay, another force came up here, so which is mu k n. You guys remember the friction force mu k n is the kinetic friction force, and mu s n is the static friction force. Everybody remember? Didn't you remember those equations, right? In statics, mu k n is the kinetic friction force. This is exactly the same equation. We're using it here. Okay, and the answers are given as well. And the final problem, I even have a sketch of this situation. You see the car is moving, right? And the normal force N is acting perpendicularly from the surface of the car where it is moving, and obviously there is this theta angle for this weight acting downward. I'm trying to remember if the theta is given or not. I don't think that theta is given. You have to find the theta. Okay, to find the theta, you have to use this equation. Okay, so tan theta equal dy by dx at x equal to 80 meter. Okay, so 0 starts from here at point A. Okay, this problem is not a straightforward problem. It's a little tricky. Okay, pay closer attention. So at point A, when the car arrives, right? If you are given the equation for the y with respect to x, right, which is here, kind of a complex equation, to find the slope, okay, to find the slope, what are we going to do? Usually dy by dx, you know that, right? And dy by dx is actually tan theta. You guys remember that from straight line equation? I don't know. You remember? No. It's a tan theta, okay? Dy by dx, the way you can think about it, okay, if you're gonna draw a line here from A, you see this is your dy, this is your dx. Does it make sense now? So that's why it's tan theta. Christian, you understand? Okay, so you see this dy by dx at point A. Why is tan theta? How are we going to find this theta? This thing, right? Then they will dy by dx at x equal to 80 meter. The reason is, you see, at this point, this equation will come and do the derivative. But here, you see, dy by dx means, you see, this dy is in this direction, dx is in this direction. So you know tan theta equal to y over x. Remember that, right? That's how it's coming. So anyway, that's how we're going to find the theta. Do you understand? It's tricky. It's really tricky to understand that, and there's some math involved. I mean, if you don't feel comfortable with derivative, please reduce all the derivatives like from math class before. Okay. If not, then on derivative definitely I can help you. Okay, and you also need to know the rho or radius of curvature. And again, you just have to. You already found the dy dx. You just have to do the derivative one more time to find the sine derivative of y with respect to x, right? So that's that. Then the rho will be here, and all the forces. I put it here, right? Is the Minkey given? No, Minkey is not given. So you'll be assuming no friction, okay? So the like, oh, there is a friction force. I put it here. Is the Minkey given? Oh, yeah, that force is given. The friction force, that what you gotta find. Sorry, friction, but the Minkey is not given, but friction force is what you gotta find. You don't need the Minkey, okay? And the normal force and the friction force. But anyway, you see, you do have this friction force and the normal force, and this 800 values given. 800 is probably the weight of the car, right? Yes, 0.8 megagram. You know, 0.8 megagram means 800 gram. You know that, right? Okay, so you know that, right? So 800 kg, I'm sorry, not gram, 800 kg, 0.8 megagram is 800 kg. So like 10 to the power 6, you know, 10 to the power 3 gram equal to 1 kg. So that's why it is 800 kg. So now, you know, this value is given. This is what? The weight. So if you know this angle from this, right? If you know this angle from this, then you know these two components of this 800, right? 800 multiplied by 8 obviously. So once you have these two components, right? So when you're going to do the summation of this a n direction, right? Fn, then you should be able to find the value of the n. Makes sense? Because this friction force will not going to interfere. That's how you're going to find these two forces. Okay? And the other one would be obviously you do the summation with respect to at, like in a tangential direction, right? Again, if the car is moving this way, did you know? If the car is moving this way, which is the tangential direction? This is the tangential direction, right? So this is the direction that you're seeing it here. These are all complex problems. One problem we're going to very well take one class. You know that, right? So I hope I was able to give you the understanding. Remember the two math problems that we did. Remember the swing problem. Even we have the same problem here, right? That and the other problems that we did before with AT and AN. If you're going to combine those, you should be able to come up with some effort. Okay, not a straightforward thing. All right, so as I'm saying, like I'm gonna upload this, and this is chapter 13 done. Okay, so we'll be starting with chapter 40, the new chapter. I mean, I do have a very interesting problem. That's what I was planning to do, but I don't feel like doing it today. I mean, that was my agenda actually, the main agenda, not this homework that I was showing it to you guys. Okay, but But what I should be doing, like, resolve this connection issue, and then, oh, you're not seeing it now. So on the recording, I was talking about this, right? So let me just one second, because I'm still on the recording. I'd like to show it to you on the recording. Okay, that was the first problem only. The second problem, I was already talking about it. So if you're watching the video, you're seeing it. The fourth problem, I was talking about it. If you're watching the video, you'll be seeing it. Number five is kind of the similar problem. Okay, so come back here. This is number five. And I do have some hints. Okay, kind of similar problem. I'm pretty sure you can able to deal with that as well. Okay, so I was showing it to you in the video. Okay, so in case if you're watching the video, let's see if I can I can make it a little bigger. So you just have to pause uh, that certain section that I'm showing it to you. I really don't want you to take pictures. It's like it's not professional. Anyway, so this way at least you have it in record, so you can use it if you want to, if you have to. All right, now come back here. Come back to our agenda for today's class. So this is chapter 14. That's what I was planning to start today. Okay, that's the main agenda, obviously, for sure. And I have a math problem. Okay, so I do have this math problem that I was planning to do as well. Okay, but I'm not going to do the math for sure. Let's talk like 5-10 minutes, whatever it takes, with this, right? And then let's end this class today. Is it okay? All right. I really don't want to jump into something where I don't have a proper control of writing stuff. Okay. So those who are watching video, the thing that I'm showing it to you guys, this thing. Okay, this PowerPoint slides. By the way, this source of the PowerPoint slide is in Brightspace. Brightspace does have everything. I have to check whether I uploaded chapter 14 yet. If not, along with the homework, this will be in Brightspace as well. But let's just start talking about it. Okay. All right, so the title itself says here, right, clearly. So we would be moving from force to work. You guys know what is work. Work is the energy, right? So anytime you have a force multiplied distance, there's a work. You remember that, right? From physics class, force multiplied distance is the work. Okay, that's what they're saying. Like the principle of work, energy, and system of particles. Okay, so there were two PowerPoints. This is one of two. Okay. All right. So moving on, you see, your goal would be calculate the work of a force. Right. Work means like force multiplied distance. Apply the principle of work and energy to particle or system of particles. So those are your goals here. I do have a quiz here, even though I have it marked here. However, in my other notes it was a little different. But let's talk about it. What is the work done by a force in this scenario? So if something is moving on this direction from S1 to S2, because of the force F, nothing is moving, right? It's in vertical direction, so the work done will be zero. You know that. So the work done always calculated along the force direction, the force multiplied the distance it traveled, right? So that is the concept behind it. If a particle is moved from 1 to 2, which is in this case 1 to 2 here, right? The work done on the particle by the force Fr will be, let me see if I can make it a little bit. So this Fr is a force here, right? Okay, this Fr is a force here. So work done only happen in what direction? Where the physical movement happens, right? Just like in the first picture you're seeing, what? Like the first image, the force is acting upward and the movement is happening what? In horizontal direction, right? So there is no work done. Understand, Joe? So, and the second problem, we do have this force has an angle. This kind of going towards the ground or wherever this is moving, right? Inside. So that means obviously it does have two components. One is the tangential component and another is the normal component, right? So the normal component, along the normal component, the particle is not moving. Where the particle is moving? Do you know? Along the tangential component, right? Remember the swing? The swing, the baby was moving on the swing like in a what tangential direction, not in the normal direction. It's not like the swing suddenly goes to the center, right? I mean, it may happen if something unusual happens, if somebody is pushed in a weird way, but usually no, right? So the same thing here. So where the force along the direction, the distance, and that is where your work consideration is only. where the distance, right? Where the distance. If there is no distance travel along the force direction, no work. Okay, so that's the concept here. That's the quiz. Let's move on. Any question with this? This should be a straightforward thing. Okay, so then obviously some of the examples here, like the roller coaster, obviously. The roller coaster has a radius of curvature. Let me read through that, see if you have a little bit more understanding. A roller coaster makes use of gravitational force to assist the cars in reaching the high speed in the valley of the track. How can we design the track? Means the height, the radius of curvature, to control the forces experienced by the passengers. Okay, and you kind of had the idea already from even last week homework, right? Like the homework that I was just showing to you, right? You had to know like some of the forces and radius of curvature comes from there, like with an as well, right? So to solve this kind of problem, you see, uh, as per like previous chapter 13 concept, you would be probably limiting yourself with only the force. When it comes here, you'll be limiting yourself with the work and or the energy. Why do you need the energy or the amount of the work? You gotta need like the motor or some other electronic means for the whole thing to move. It's not like it's moving by its own force, right? So you need the amount of energy. So that's why the work done is needed. Work done is ultimately amount of energy. It makes sense. So that's why this chapter is important. Just to highlight the importance of this chapter, why you are suddenly moving from force to work. Okay, the work energy is all related. You just need to know the distance because of the work, so because of the force, how much it traveled. So you can kind of use those things together. Okay, let me try to go same way on this slide. So on the recording, it will gonna show. There are other applications as well. I really don't want to spend that much time with that. I'd like to focus on these equations that we're seeing it here. Okay, a little bit more in depth. See, this one we have seen where, like, in quiz second question, right? The same thing. Remember, I was emphasizing on when the force is applied on certain body along the direction of movement happen, would be obviously exploring the work by multiplying the force and the distance. Okay, so what we're seeing here, the equation of motion with respect to displacement F equal to ma, and then this at and ft can be deduced from the summation of forces along the tangential direction. We have seen that thing before, right? So we have seen that thing before. Okay, so then this AT, how many of you remember this AT is actually V dV ds? Everyone remember that from first few weeks, right? So you might have to use that for equations, okay? Then principle of work of energy. I'm just trying to highlight if there's something important that I can share. Here's basically all it says here. Previous chapter thing, okay? But this is where the new stuff came up. Once you have the force already known, then you can use the integration, and that's kind of overreach. You may not have to do integration. Most of the time, you just have to find the force first by previous chapter concept and find the distance, and then do the multiplication to find the work. Okay, but in a complex scenario, as per for theory, they have to show it, so they are showing it this way, or or okay, let me see if I can put it here. Or if you are dealing with the software, right? In software, they always have this thing in finite element. You heard about finite element? Finite element. So they always embedded the code in finite element to calculate this work, okay, in a complex scenario in software. But analytically, usually you are not capable. Usually, okay, we don't explore it, right, to deal with the complex problem analytically. Okay, that's why we always go into software. Now, analytically, why is like we're learning first of all to learn the first principle, right, the detail of the knowledge behind it, and other reason analytical thing could be important. I don't know if you ever exposed to it. How many of you are in substance here? Anyone? No. Class project? No, not yet. So, like analytically, the best way of thinking is always make things simpler by using assumptions. Always remember that. Okay. Say like we are dealing with the curvilinear path, right? So maybe you consider a section of it and use the circular section and somehow get the circular equation. It's easy to get circular equation, and then you can get some assumptions based on that section only. Okay. I mean, I don't know, situation arises, but let me move on. So this is the generalized case as I was explaining. If you are in a situation like that, you see where the ball is moving along the curved line, so you have to do the integration because at every moment the displacement is changing, the force is changing. Does it make sense? So that's why you have to do the integration. That's what it's showing here. Any questions so far? A theory not. I know you're gonna have that much question. So this is like something that you would be possibly seeing most of the time. Okay, Delino, you see here, whenever I mean, you see, this has a curve. So this one has a curved line, right? And if you'd like to solve the energy for this force F, okay, and then you gotta deal with this. You see, this force F has this component in x direction, which would be F cos theta, okay, and then you'd like to do the integration from s1 to s2. In that case, you need to know the force equation in terms of s, right? Understand that? So that could be a complex venture. Maybe you don't have any clue to find the f equation in terms of s. You should understand what I'm saying, right? Did you got it? So, and obviously this is the thing you may not experience, and I'm saying, like, maybe this kind of thing will be experienced in software. Okay, so software will do that, but most likely will be most of the time deal with this kind of thing. Okay, do some assumption s1 to s2, and then f cos theta you'll be using, and then get the value of this energy from 1 to 2. Let me see. Okay, so this one is important, and the math problem that I had actually planned to do today had this spring. Okay, you guys remember the spring force? Some of you remember the spring force. What is the spring force? If spring constant is k, and the displacement is x, f is what? Kx. Remember, everyone? And the spring energy. That's the thing you may not have seen before, right? Half of kx squared. Okay, so it is. Yes, half of kx squared should be somewhere here. As you can see, half of kx squared, right? So x is what? Distance. Here, Joe, what is the distance? Usually we refer it by s1, s2, right? Those kind of thing. S for position, and then there's a distance. So anyway, so see what is happening here. This u1 to 2 is referring to the work done on a particle by spring force will be what? Will be for this spring displacement from position s2 to s1, right? And we'll be using half of k is the spring constant, you understand? S2 square minus half of k s1 square. Does that make sense? So in other words, think this way. Say like this is spring, right? So initially it's in compressed situation, right? And then at that situation, this position is s1, right? This is just the whole spring length, but this position is s1, right? And then the energy at this compressed state, right? Which would be what? If the spring has a spring constant k, then it should be what? Half of k s squared. You understand that? And then Brett comes here and push it so far, it comes up to this point now, right? There's a new location s2. So then it would be like half of k s2 squared. So that's the new state of energy. So now to get like how much of the energy get involved for the spring to stretch or compress, whatever it is that is happening here, this is the equation that you'll be using, right? That's the amount of energy required. So bottom line, half of kx squared is the energy for spring. Okay, this 2 s1 and s2 for two different locations. Any question? That is important. You will be using it in next class for sure, right? What else? Let me see. Work of weight. It's kind of the similar concept, right? No. What is the weight here for this thing? The mass multiplied g. You know that, right? But when I'm putting it here, right? Is it moving down, penetrating? No, it's just sitting here. So no work done because of no movement. Just the thing concept is running out there. So if you have a weight which is it's a dynamics class, right? Which is constantly moving down. So because of the weight, the amount is moving down along vertical direction, right? The y2 minus y1, that's why. So you can find the work done because of the weight is the blue is here is the mg that I was talking, right? Multiply the distance y2 minus y1. Got it? Okay. Then it didn't end here. It has more stuff. Okay. Um, that's the last one, by the way. So work of friction caused by sliding. So there's this friction happening here, right? And friction again, the same thing. Okay, the friction it's a mu k because it's dynamics, right? Mu k is the coefficient of friction rate. Kinetic coefficient of friction. Remember that, right? So mu s is what? Static coefficient of friction, right? All right. So then this is the force, obviously the friction force. Okay, and then the principle of work energy would be applied as, so you'll be considered the whole thing. Okay, so here obviously the P is the external force, weight W, normal force, and the friction. All four of them we're counting here. Okay, in terms of energy. So that's what this is, principle of work and energy, right? So now how are we going to deal with that? Okay, so this P, because of the external force, right? It has a movement of P multiplied S if it moves along this direction, right? And if it moves along this direction, as you can see from here, this is the S distance it traveled. This is the velocity V, right? So this velocity, you see, because of the weight of this block, if it's like 0.5 gram or whatever, right? No, sorry, m. It's half of mv squared. You remember that equation, like kinetic energy equation. So because of this block movement of velocity v, we have this amount of work or energy involved, which is again half of mv squared. Remember kinetic energy. Remember that equation for the kinetic. What is the potential energy? Mgh. Remember. So that's for this block to move, right? And then this external force P applied here, and this movement happened as. So that's why you are multiplying this P multiplied as. Again, this is the work term, right? And this mu kn. What is mu kn again? Is the friction force, right? And it's happening opposite to the movement direction. That's why you have a negative here. Okay. And when it moves from this point to this point, as distance traveled, the same thing happening with the friction as well, right? When it is moving, whatever distance it traveled, the friction happened among the same direction, right? Same amount of travel distance. So that's why this S is over there. All right. Finally, you have this equal to half mv squared as well. So this whole thing ultimately moving. So remember the summation of fx. That's the way you do always. So the whole thing is ultimately moving at velocity v, and then coming up with that. So basically, it just says this value and this value is same. Okay. Anyway, that's the force balance. We'll be doing so many math problems, especially this math problem when we'll be doing in next class. So two things from my side, I'm gonna make sure. So especially when you're gonna doing this math class, you'll be applying. I'll be applying everything, so you'll be probably seeing everything. For my task, what I'll be doing, I'll make sure all the materials for chapter 14 is in Brightspace or not, and I'll also upload the homework number 6 in Brightspace, which you can do on and try to. Okay. And sorry for the technical glitch. I'll resolve it before next class. Okay. At any cost. Hey,